All right, moving on. We're going to talk about parallel versus array jobs. Harder, better, faster, stronger. So yeah, the big promise of high performance computing is like make it better, make it faster. And then everybody wants to immediately make everything parallel. What is parallel? Well, parallel is, spoiler alert, it's hard. You just can't take the code you've been running on your laptop or somewhere else and then put it on and make it somehow magically parallel by running on an HPCC. It's still going to have all the same limitations. You may be able to throw more RAM at it, but that's not going to help because the way you use RAM, unless you're using it efficiently in the right way, it's not going to magically use more RAM efficiently somehow. It's not going to use more CPU somehow more efficiently. You actually have to think about this in ways that makes sense for the HPCC environment and for any research resource you use, really. If you've got a department server, you got your laptop, how many cores are there, how much memory is there? There's that cluster over at the other school, like how do their job scripts work and how much memory are we allowed to have, et cetera, et cetera. So parallel is usually referred to in HPC, in research computing as MPI, which is message passing interface. And it's really hard because it's a way of running multiple threads on multiple cores on multiple servers, aka the compute nodes. And MPI is the message passing between all of those different threads on all of those different cores scattered on many computers. And that communication between those threads has a lot of overhead. And unless you are specifically programming for that communication, for those border conditions, for those interprocess, for the file access alone, all those threads accessing files in parallel can really mess things up. So unless you do all of that and you are an MPI programmer, or you're using a toolkit or a solver that has already been programmed to do that, it's not going to work well. And even if you do have a function or a piece of example code that is parallel, on the HPCC with an optimized code, we typically do not, this does not scale linearly. Like if you do 2 processors, you may see like almost a 2x speed up. If you do 4, you might see almost like a 3 or a 4. And if you do 8, you might see like a 5 or a 6. It starts to flatten out there. And once you get to 20, it's just all the overhead is just wasting resources. So please don't start a parallel job and use as like 64 or 128 cores and expect your code to run. It's just wasting resources and it'll actually take longer. So that's my spoiler saying, like, just don't jump to parallel. It's hard and it doesn't work well.
And let me say, can I say one thing about that too?
Yeah, please. Just
get in touch with us for parallel stuff. That's my biggest tip, because we've done a lot of it, and it depends on what you're doing. Some stuff scales better than others. If it's completely, if they're disassociated, you can get some pretty good scaling. But again, like Gavin said, it can be pretty hard. Yeah. So just get in touch, reach out. We love to try to figure these things out.
Oh yeah. Oh yeah.
And he's going to talk about the better solution shortly anyway. So
yeah. Like he was saying, like there are some use cases like a Monte Carlo simulation that scale really well. They're called embarrassingly parallel because there's not a lot of border conditions that can hold up the step of the progress of a parallel code. But anyway, let's move on to what we really recommend you do is an array job. And these can be really easy. So say you have a code on your laptop and it runs really well over one subject or over one time step or over one data file. But you've got 1,000 files, or you've got 30 subjects and it takes like 10 hours for each subject. Or you want to run the same code, but you want to try to use 100 or 1,000 or 10,000 different starting parameters or seed values. These are all really good use cases for an array job. An array job uses one piece of code and will start with either different data files or different steps or different seed values. And those are all keyed off of the SGE task ID environment variable. So what you do is you write a script and you either reference the SGE task ID there, or you write it in your code as the environment variable SGE task ID. And that can be a key into an array. It could be the nth data file. It could be the nth subject. And so if you are able to write your code in such a way that you can reuse the same code over and over, like on different values that are keyed by that one variable, then you could run up to 128 of copies of your code on all the different subjects and all the different files. Or if you manage to write your code in such a way that it can complete in under 4 hours, jobs on HPCC that run in under 4 hours are eligible for the short queue, and we reward you by giving you possibly twice as many running slots. So you could be running over 200 copies of your code. If you have like 1,000 data points, you could be running 200 of those at the time. So that's like, that's like a 200x speed up. It's literally like a linear 200x speed up because you're running separate copies of the code on all those different values. But there's some caveats there, right? So they all have to be keyed off the SG task ID, and that's just a range from one. Say if you choose 1 to 1,000, it would be 1, 2, 3, 4, 5, 6, 7, all the way up to 1,000. And each time the code runs, it would just key off of 36 or 212 or 7 or 982, like whatever that SG task ID variable is, the rest of your code runs. So it's a little bit like a loop, but it's completely decoupled. It's not like a loop where you can have where it's serial. That's one of the caveats here, is that you can't have serial dependency in your code. Like, this is not a loop where it's going to be like, okay, run 1, okay, save output, run 2, load the previous output and append this. You can't do that with the array jobs. The array jobs have to have no dependencies between the loops. It's not really a loop, it's just different tasks. And it has to, if it's writing files, it has to write to separate files so that they don't stomp on each other. So that, task 2, task 3 doesn't write over task 2's files, and et cetera, et cetera. And we do a little bit of checking to make sure that doesn't happen. So it's not too much to worry about. And there are no shared variables between that you can pass between these tasks other than the iterating SG task ID. And like I said, separate output files. So I'm gonna show you a very quick example of running an array job. If you didn't know, when you log into HPCC, you can go to user local demo directory, and we have demos for all of our major software packages. So I'm just going to go into MATLAB here, and you can see we have different demo codes here for MATLAB, and in particular, we have a directory called array jobs. And you'll notice there's a README there. So I'm going to less the README, which is will show me the file. So we can copy, so it says right here, we can copy this directory to our home directory, and then we can launch jobs depending on how we want to do our array. So there are two examples here. One is keying to variables in a CSV file. So for each iteration of the SG task ID, it's using line 1, line 2, line 3 of that variables.csv file and using those variables as parameters to our code. So if you wanted to have 1,000 different parameter sets to your code and run your code 1,000 different times, that's the way to go. And the second one here is we're reading data, and for each iteration of SG task ID, for each task, we're reading a different data file. And those data files live in a directory, and it counts them, and it will use the SG task ID data file. So what we want to do is copy this to our home directory. I'm just copying that command, Q to quit less, C to my home directory, and I think I might already have that here. Let's make sure. Not my old one. I'm going to copy recursive the array job directory to my tilde. Tilde is my home directory. So now, in my home directory, I have my own copy that I own, and I can read and write of the array job example script. So I'm going to go ahead and I'm going to open this in the terminal Vim. So forgive me, I'm not using code here. I'm using an editor in the terminal. So you can see that we have. I'm going to do the read some data example. So if we look at this job script, it starts with a bang. It's a bash script. We're joining our standard error and standard output, so it's all of our outputs in one file. And we're giving it a name. We're naming the job task array. And we're creating a variable saying data is data. And we're saying this little script right here in the string, in the parentheses here, this will assign the output of this command to data file. So what we do is ls the data and we're piping it to the sed command, which is a Linux command, -n sge task ID, p. And this may be a little cryptic, but what this does is takes the directory listing of all the files and pipes it to sed, and sed will only print the nth line of that listing. So if we're on sge task ID 1, sed will only show us the first file in that directory. If we're in sge task ID 2, it will only show us the output and print the second file in that directory. So that's a pretty good trick. And then we're just echoing in the terminal to say a little informational message that will show up in our output script, our output of the job, saying, starting task ID whatever on our data file, which has that path. And then we're launching MATLAB. This is how we launch MATLAB from a script. We say no display because we don't have graphics. We just have a script at the command line, and we're going to run the function, read some data, and the data file. So we look at read some data.m file, and there is a very simple read some data function, and with the parameter data file that we passed from the script. And it will say my data equals read that data file. And I think the T, I believe that's the separator, the tab separator. Anyway, so let's go ahead. If we look at that README file again. So we copied it to our directory, we seeded it in there, and we're going to run the import data job. So this is the command right here to run this script. So we're going to qsub, and the T is the task array option, 1, 2, and then this is a little cryptic again. We're using the output of this command here as, I'll just show you that. If we run that command, we're doing ls data, and we see that we have 1, 2, 3, 4, we have 10 data files in there. And then we're piping it to the command line word count on lines. So if we did that, actually this is a little confusing, but anyway, when you pipe it, it looks like that. So that's the listing of the directory. We pipe that to word count -L for lines, and it tells us there are 10 lines in the output, aka 10 files. So that would be 10. So in this command, everything in these parentheses is 10. So just to be clear. So we're doing qsub -T 1-10 read some data. There we go. Job array has been submitted. I can see, oh, look, they're already running. So qstat shows me they're already running. And look, there's almost completely done. And they're done. And we can see now we have output files in this directory that are named the job name.o for output, the job number, the task ID. And if we look at any one of these, they're probably going to be very similar, except they're different because they're each using a different data file. So let's just look at the first one. So this is the MATLAB banner, and then my data is the data that was in the data file. So you can see here we can quickly build up, whatever your data is, all of your functions, and you can run them all simultaneously. We just ran 10 at a time simultaneously. That's a 10x speed up. I think that's a big win. And obviously that can scale up to 128 or 256. So that's great. Before we move on to Python, does anybody have any questions about array jobs or tasks or the SG task ID variable?
One other thing to remind you guys of it is that's very cool about array jobs compared to parallel jobs. Parallel jobs, let's say you do a short queue parallel job of 200 cores and you're like, yeah, that's going to be awesome. It's going to be so fast. You're requesting 200 cores. The job will not start until you have been assigned all 200 of those cores. It might take 3 days for you to get 200 cores on our 512 core box. Whereas if you run a 200 core short queue task array job, if there's only one core available, that first task is going to start right away, which is awesome. So and it'll just keep filling them in. It'll, they're all sort of trying to start. So that's really nice. And in fact, what's also cool is you can intentionally just, if they're shortish jobs, we recommend that you do maybe the first couple of tasks, -T1, -2, to test your code
yes,
before you start the 100,000 task array job.
Mm-hmm.
I think the biggest downside to an array job is if you do need to do 100,000 of them, you will end up with 100,000 output files, which you'll then have to do something with. So that can be challenging, but we know great ways to deal with all that stuff. So get in touch.
Oh, that reminds me, Hugh. Thanks. Another tip is that if your tasks only take a couple seconds, they're going to have so much overhead starting and waiting and trying to get jobs. It's not like the overhead of starting a job maybe like 15, 30 seconds. So if your task only takes 2 seconds, you've just made your job take 16x as long. So if your tasks are only, you want to break up your work in a way that is at least running for like maybe a minute to an hour, something like that. Under 4 hours would be optimal because then you can put it in a shorter queue. But it's okay if it takes 10 hours for each iteration. That's okay. But yeah, don't make it, yeah. So the shorter your job can run, but don't make it seconds, because if, in that territory, you're just losing time on job start and overhead. Our job queue, that when you submit a job with the queue subcommand, it goes into our queue, it waits its turn, it runs very efficiently, but there's still some overhead there to get them running. Okay, so.
Yeah, I may have a question about the array job.
Yeah, sure.
Yeah, so say we have this, we get 200 jobs and submitting an array. Do they actually run concurrently? So I think it might use, leave less resources for other users in the group, right?
Yes, they will all run simultaneously, concurrently. If the cluster is not very busy, you may get 128 tasks running at the same time. And if it's really busy, you may only be able to get like a couple dozen running at a time. But yes, they will all run at once, and they'll complete as efficiently and as soon as resources are available, as CPU and memory become free from other jobs.
I think what you're implying, though, is yes, if you're working in a team of 4 and you're all working today and you're all running jobs, if you start your 200 task array job and each task takes 2 hours, and you start it before user B, the other person in your team, starts their array job, your job will have to complete before their job will be able to start. So if you are working together in a busy way like this, we have some tips and tricks for you. Just get in touch. There are ways for you to limit the number of jobs, concurrent jobs that you have running. It's the TC option.
Yeah, aptly named.
Yeah, task concurrency.
Mm-hmm. Yeah, so if you do -TC 16, you will only run at most 16 jobs at a time, tasks at a time, and then that'll leave room for your other team members to get some things in.
Yeah, thank you. Also, thank you for asking my previous like random ticket questions.
No problem. It's fun.